Let me show you a rational equation that is actually a bit of a simpler variety, simply because of where the x is, but it will give us an idea of the technique we're going to use when it comes to this denominator. So x over 6 plus 2/5 equals 1/3. It's a rational equation, but you'll find out it's not too tricky because the x is not in the denominator. But it gives us an opportunity to talk about something. When you look at this from some prior knowledge, I'm wondering if you can think of a number that you would like to throw at this equation, a number that you would like to multiply the entire equation by that would clear the denominators. To clear the denominators would be to cancel the denominators. Are you thinking about a number? It's just a good old number. And how did you do? It should be the number 30. Now, if you're saying, I got that, you probably feel kind of good. If you're like, I don't know, I wasn't thinking of the number 30. Just hold on, because I want to talk about the number 30 with you. Okay. One thing about the number 30 is it actually is the common denominator. We actually typically call it the least common denominator because it's like the smallest number, but it's actually the common denominator. And so how does that change the way you approach that number? You could look at 6, 5, and 3, and you could deduce the common denominator of 30. It also can come from thinking of the factors of these denominators. Now, what I'm about to do, some of you might think is a little overkill, but it's going to be really helpful when we get to an algebraic problem. So let's think about the factors of 6, if you will. They're just 3 and 2. Now, the factors of 5, well, it's already prime. It's already factored. I mean, we could say 5 and 1, but the truth is it's just 5. And it's actually the same thing with the number 3. The factors of 3, well, it's really just 3 and 1, but 1 doesn't need to be mentioned. Now, why am I doing this? Why am I kind of splitting up into factors? Well, because this number 30, this LCD, needs to contain these factors. And I want you to watch how I make it contain it. It needs to contain a 3. So I'm going to put a 3 down in my LCD list. It needs to contain a 2. So I'm going to put a 2 down. Now you'll notice that I'm multiplying those as I put them down. It needs to contain a 5. Okay, so far nothing too fancy. We're basically saying that, geez, we need to have these factors. Until we get to this 3, and this is kind of why I'm doing this, the LCD needs to contain a 3. Does it contain a 3? Yes, it already does contain a 3. So I don't need another one. Okay, otherwise it wouldn't be the least common denominator. Now again, you might say that's a little overkill, but just look, 3 times 2 times 5, bingo, is 30. That's going to be really helpful when we get to an algebraic problem, one that has like x's and stuff. Let's multiply 30. And I want you to notice how I'm using 30. It's interesting. I'm not actually writing it as the common denominator. No, I'm actually just multiplying it. I'm multiplying it to each numerator. You're allowed to do that. Okay, nobody said it has to go in the denominator. In fact, I don't want to put it in the denominator because I want to cancel. So I'm very carefully taking 30 and multiplying it to each numerator. Now, there might be a time, maybe it's already, that you would do this mentally because maybe you can already see that 30 and 6 cancel to be 5, of course, x. And hopefully you can see here that 2, 30, and 5, they cancel to be, well, 12. Notice, though, of course, that the denominator is gone. That's the whole purpose of this. And over here, obviously, we get 10. Bye-bye denominators. Bye-bye rational functions or rational equations. Okay? And again, I told you when we started this, it's a little bit of an easier problem. I hope that you can subtract 12 and divide by 5. And we end up with negative 2/5. Rational equations, okay, they require a careful consideration of this multiply by the LCD. Write it down, read it, whatever you're going to need here. But I want you to realize that we always multiply by the LCD. When you do that, you actually multiply it to the numerators. That's good multiplying to the numerators. Now, I've thought long and hard about this, to be honest. What is the easiest way to try to describe this thing called the LCD? Now, for some of you, you don't even need it described. You just kind of need to think about it. But I do want to put down in words this idea of having all factors represented. I've tried to make that make sense. Think about that with me. All factors have to be represented. That will be the main thing that we talk about through the next couple examples, because if all factors are represented, then the LCD is going to do its job. It's going to cancel. But there might be a time where you guys sort of goof up the LCD. And if you goof it up, stuff's not going to cancel like it should. There's also a possibility that you will have more than the LCD, like you'll have more common denominator than you need. If that time ever comes, you're going to find yourself with like too much X. And I know I'm saying some things that you might be like, I don't get it. But you get to a problem and it just doesn't seem to be working. I want you to reconsider, did you have all the factors represented? Not overrepresented, not underrepresented. Let's see if we can kind of obviously think about this through some problems. The whole check thing, it's still on the table. You still have to check. But good news, you only have to check for a 0 in the denominator, which really means you don't have to go back and do like a full check. I'll show you when we get to some problems. Here's a rational equation that's a little more algebraic. And simply, it's because x is in the denominator. When x is in the denominator, you're going to have to employ this method that I'm trying to teach you here, this idea of an LCD. Now remember, if at any time you become a kiddo that says, I can just kind of see the LCD, then that's fine, just see it. I want at least a few times to help you think about the factors, and I'm going to write them down, and obviously you kind of do what you want. I'm insinuating here that the factors of x squared would be x and x. Yes, you need like both of those x's to satisfy the factors of x squared. The factors of 4. What we're really doing here is breaking it down to like its prime factors. So, we can jump right to 2 and 2. And then the factors of 8, x. Maybe there was a time where you did like a factor tree. Kind of what's going on here. We're just doing a little faster. But the factors of 8 would be a triplet of 2's. And, well, don't forget about that x. And this is a great example for us to make sure we have all the factors represented. And I'm going to kind of go through it sort of from the beginning. Okay, so I need an x. I actually need another x because I need both of these x's represented to be able to satisfy x squared. So I actually need an x and an x. I'm going to leave a little space here for our final answer, which maybe some of you can see already. Now, I need a pair of 2's. Yes, you need 2 2's represented. And then we get over to this last one. Now, maybe you have an idea what I'm going to say here, but this says that we need 3 2's represented. We need 3 2's. As I look over here, I say, well, I already have 2 2's, so we just need one more. Okay, I only need one more because, again, I need the least amount. It's the same thing with this x. I need an x represented. It's already represented. Take your pick, either this one or this one. Now, if you're like, why don't you put another x here? If I put another x here, I'm getting into this territory where I have too much common denominator. And basically, that's going to cancel. It's going to over-cancel. And you're going to end up with an equation that has too much x. Okay, so bottom line, 8x squared. 8x squared is sort of your magic LCD. As you catch on, you can apply these strategies as you want. Some of you are going to say, can I just jump right into this step? Yes. Okay, yes, you could jump right into this step where you multiply. I like that you're doing it on your own. You're welcome to look up here. We're not going to do a ton of these, and I'm going to give you an exit ticket shortly. But let's make sure that we cancel. This is a key step. We're going to cancel. You know you're right if the denominators are canceling correctly, which means that they completely disappear. So that's a check. Over here, the 4 is going to cancel. That's a check. And over here, if we're careful, the 8x cancels and just gives us x. Hidden behind every one of these problems is an equation that's not rational, like a good old, in this case, polynomial equation, that wants to equal 0. So let it do what it needs to do. Let it equal 0. I don't like 2x squared. I don't like the leading coefficient to be negative, so I decided to bump everything to the other side. Okay. Similar to the homework problem that was asked about, probably the quadratic formula. Unless you want to complete the square, okay, you could complete the square, but I'm going to not do that because, again, I see this leading coefficient of 2, and it's not going to factor real nicely off of this x. Basically, it's going to leave us with a fraction. Okay. Now, when you do the quadratic formula, you get the opposite of 1, plus or minus, the whole square root thing. It's actually called the discriminant. Maybe you just studied that in algebra. The discriminant comes out to be 65, and it's all over 2a, so it's all over 4. Yes, I did kind of just jump down to the answer. I'm assuming that you guys can get 65 if you need to. Now listen, that answer isn't pretty, but it ain't going to give you a 0 in the denominator either. What do I mean a 0 in the denominator? Well, there's only one number that if I plugged it in right there would give me a 0 in the denominator. It'd be a big old 0. Same thing here. So I'm pretty sure this isn't equal to 0. It should be right. Okay? You don't have to officially go back and check anything else. Thoughts? Okay, now the next example, it's kind of purposely going to feel a little different. I'm trying to show you guys as much as possible, yet it still is rational. So it still uses this LCD method. X plus 4 over x, 3 over x minus 4, negative 16 over x squared minus 4x. Maybe you kind of want to still listen. The denominators are a little different. We're still going to think about the factors of the denominators. Okay, this guy, it is the factor, and so is this one. Now that might have caught you, maybe surprised you there, but when we think about a factor, in this case, it's a binomial. We take the whole thing because this is able to be factored into essentially the same two things. See how we want to think about factoring when we have things like binomials. Okay, I'm not going to separately split up the number 4. Again, over here, I actually factored out the x to get x minus 4. Okay, now your LCD has to have an x. Your LCD has to have an x minus 4. And this one says that you have to have an x and an x minus 4. Are you thinking about that the right way? This one says I have to have both an x and an x minus 4. Well, I already have them. So I don't need more. I don't need another x or another x minus 4. This might be a problem where you're ready to do this. Maybe you're already doing it, but if you just want to listen, this thing right here is going to multiply to all three of these numerators. I don't really want to rewrite it 3 times, but I can already see that this x is going to cancel with this x. So that means that I will only be left with the yellow x minus 4. Don't forget the white x plus 4. See how we can do the same thing here? This x minus 4 is going to cancel with this x minus 4. That means I'm going to be left with just the yellow x. Of course, the number 3, nothing happened to that anyway. Fully cancel. Fully cancel. So only left with negative 16. And I hope I didn't ruin your fun there, but that's certainly a fair game. You guys could do some mental canceling. Finish this one. It's a good problem to finish. In case you're curious, yes, that is correct. Okay, so it's more of a simple factoring. We call it like a Gcf factoring. As you proceed to find, in this case, your 2 solutions to be 0 and negative 3. But, okay, so now what you want to understand here is that all you really need to do is see if when you plug in 0 into any of these x's, if you get a 0 in the denominator. Well, it doesn't take too far to get into it that you say, well, I can't plug in for that x. So right away, that nullifies x equals 0. Sometimes people will incorrectly conclude that 0 can never be an answer. Okay, it just depends on what the denominators look like. By the way, the number I couldn't plug in here would be the number 4. So I think I'm good. Okay, but all you have to do is check to see if you have a 0 in the denominator when you plug in. One more, and then we're going to give you another lovely exit ticket. This one I have on paper to make it a little easier for you guys to work it out. Four over x minus 2, 1 over x plus 5. Before you jump too far into this one, let's pause a second. Remember back in maybe like junior high or so, you were probably working with some equations. It was probably a fun unit. There's no reason you can't do that again. Everybody seems to like to cross multiply. It's something that it's a great skill. It only works though if you have a single fraction equal a single fraction. But yeah, I mean, you could cross multiply. Do you realize in essence what's happening is you're canceling each of the 2 denominators. You're canceling, but it's just easier to think, oh, geez, just cross multiply. Again, you can only do that if you have 2 single fractions that are clearly equal. Okay, but that might be a quick shortcut, an easy way to solve an equation. Okay, some pretty easy algebra here. Maybe we can do a couple steps together. 4x minus x is actually 3x. 20 subtract 20 is actually negative 22. And clearly we get negative 22/3. Well, this is kind of a day one. There's actually going to be 2 days of this. So there's a little more to this, but what I've given you is the main idea, but there's more equations to kind of expose you guys to. And truthfully, this exit ticket actually does some of that. I'm not saying that this is hard, but there's going to be something in this exit ticket that will make you think about this LCD method. It's that number 1 that's just kind of hanging out there. It's kind of lonely. There was a song that 1 is the loneliest number. But I'm telling you, be careful about that number 1. Maybe right now you want to write it as 1/1, so that you kind of make sure that it becomes part of the method that we taught you. So you might want to think of that 1 as 1/1.